Let's look at step 6 of the root locus, determining angles of departure. From the poles and angles of arrival at zeros. So we're going to do this live. If somebody else comes into the office and asks a question, I may have to push pause. So in a sense, our approach is the following. Every point on the root locus must satisfy that the angle of GOL of S at that point is equal to plus or minus 180 degrees. So this is our rationale. To determine the angle of departure or arrival, we choose a point. If we have a point here that marks a zero or a pole, let's go ahead and do it as a pole. So if we have a point here that's a pole, we're going to choose a new point which is epsilon close to this pole. So we're going to make it really close so that the difference is epsilon away, where epsilon is pretty close to zero. So then we're going to solve for the angle at the epsilon value. So what is GOL of S1 plus epsilon? We're going to look for this angle. So that angle is going to tell us, relative to minus 180 degrees, how the angle is going to be either departing or arriving. So let's revisit our original running example that we have going on here. Here we have GOL of S is equal to S plus 1 over S times S plus 5. We're going to have another pole here, S plus 2 squared plus 4. So this is not the same transfer function that we've been using. It's a little bit more complicated of a transfer function. So we're going to have to do a bunch of the individual pieces for the other parts of the root locus in order to make this one actually work. So I'm going to copy this GOL of S here so we can use it later, but I want to go ahead and identify what our pole values are. So if we look at this, we actually have a 0, Z1, which is at S equals minus 1. And then we have a couple of different poles. So pole 1 is at 0. Pole 2 is at minus 5. And then we have two poles, 3 and 4, which are at minus 2 plus or minus 2j. Or plus or minus j2, I should say. So if we go ahead and take these pole values, we're going to plot them on the PZ map and do phase 1 of the root locus. So let me go ahead, let's do a background here so that we can, there we go, I like that one. So I'm going to go ahead and paste GOL of S here so that we can remember what our transfer function is. And I'm going to try to do a lot of this in one corner so that we can keep our working space over to the left fairly isolated. So now, okay, let's go ahead and always identify our axes. There's the real, and there's the imaginary. Okay, so let's go ahead and indicate our poles and zeros here. So we have a pole at S equals to 0. We have a pole at S equals minus 5. So I'm going to call this minus 2, minus 4. So we have a pole here at minus 5. And then we have two poles at S equals minus 2 plus or minus j2. So that's one here and one here. Alright. And so now we also have to indicate that we have a 0 at -1. So here's our 0. Okay, so step 1 is identify the regions of the real axis where the root locus will be. So here we'll have the root locus here because we have only one pole to the right. And then as soon as we find the 0, now we have 2 on the right. So throughout all of this region here, until we get to the next pole, we're always going to have an even number of poles on our right. Because as soon as we pass this pair of complex conjugate poles, those poles are still an even number. But then when we make our way to the pole at -5, the root locus is on the real axis and heads off towards infinity. So again, this pole starts at the pole, or sorry, this part of the root locus starts at the pole and heads towards the 0. So now we need to calculate what happens to this pair of complex conjugate poles. So we've already drawn the PZ map. That was step 1, PZ map. Step 2 was real axis segments. We've done that. For step 3, we need to calculate the asymptotes. So to calculate the asymptotes, that breaks down into 2 pieces. We need to calculate sigma A, and then we need to calculate all the values phi sub A. So sigma A, as you'll remember, is the sum of the poles minus the sum of the zeros. So we have a pole at 0, we have a pole at -5, so we add -5, and then we add -2 minus J2, and then we add -2 plus J2, and then we subtract our 0, so we're going to subtract -1, and divide it by the number of poles minus zeros. So we have 5 poles on the bottom. Is that right? Oh, no, sorry, 4 poles on the bottom. So 4 minus 1. So this gives us our value sigma A, because these J2's will cancel. So -9 plus 1 is -8/3. So that's our value for sigma A. The value for phi A we do for 3 values of k. So we're going to do it from k equals 0, 1, and 2, but we don't do it for 3 because we're looking for only values k less than or equal to n minus m minus 1. This is the range over which we look for k. So phi of A again is 2k plus 1 over n minus m. And so now times 180 degrees. So for k equals to 0, this gives us phi A of 1/3 times 180. And then k equals 1 gives us 3/3 times 180. And k equals 2 is 5/3 times 180. So these values again are 60, 180, and 300. So now we're going to indicate the point -8/3 over here on the graph. So -8/3 is almost -3, but not quite. So it's going to be somewhere right around here. So this is the value real sub A. And then we need to make 60-degree angles coming out. So 60 degree is the angle that you get from a 3, 4, 5 right triangle. So if we're at about -3, then we're going to be at about +4 coming up. So that value it's going to cross is going to be about right there. I'm going to go ahead and draw this using a slightly different color here. We'll see how well this shows up. So there's one asymptote. The other asymptote in this direction. That seems about right. So those are our asymptote values. And we know that the pole is, the root locus is going to approach that value as it heads off from its complex conjugate pair of poles that we see here and here. So now we're going to try to determine whether or not the system crosses j omega. So we could do that, but I'm actually going to skip it because I want to talk about the angles of departure. So again, part 4 is for j omega axis crossing. So we're going to skip that here. Part 5 is where we calculate the breakaway point. So what's the breakaway point? The breakaway point doesn't really exist here because the two poles are already off the real axis. So the breakaway point for this particular example is not applicable. So the next part that we're going to calculate is the angle of departure and angle of arrival. So 6, angle of departure / arrival. So we're going to start now with angle 4. Let's go ahead and label these values. I'm going to call the one at the pole S1, or the pole at 0 S1, and then we have S2 over here, S3 at the bottom, and S4 at the top. I'm going to call the 0 S0. So let's start with angle 4, because again, we don't really need to calculate angle 0, angle 1, and angle 2. We're going to calculate angle 4, and then we'll be able to get angle 3 by symmetry. So at angle 4, if we wanted to actually calculate how this value is going to be, we know that if we add angle 0 minus the angle of S0, which I'm calling angle 0, minus the angle at S1, minus the angle at S2, minus the angle at S3, minus the angle at S4, we know that this is equal to plus or minus 180 degrees. And we know this because the point has to be on root locus. And so now we're going to go ahead and pick the actual values of angle 0, angle 1, angle 2, angle 3, and angle 4 from the point S4 plus some value epsilon. So that epsilon value is going to be small when we're far away from S4. So let's go ahead and calculate angle 0. Let's remind ourselves where these points are. So the angle of 0 is -1, 2 away from the angle S4. Right? So if we look at S0, it's at the origin. S4 is at -1, 2. So if we calculate that angle, we can actually do this just by demonstration on our calculators. So you can take your calculator and in Cartesian form just enter -1, 2. And then display it in polar form to get the answer. But make sure you're in degrees. There we go. All right. So in degree form, that angle is 116.56. So if we look at the angle 1, again, now we're looking at the difference between where S1 is and where S4 is. So the difference here, because S1 is at the origin, is at -2, 2. Remember, S0 was here at -1, 0, and S4 was at -2, 2. So that difference was -1, 2. Okay, so the difference between the point S1 and S4 is -2, 2. So you can probably do this one in your head, but the angle is 135 degrees. So remember, we're not measuring the angle this way, right? We're measuring the angle from the point S1 until we get to S4. So we're measuring this angle, which is 135 degrees. So the angle 2 So now we're going to find the point S2, establish the difference to S4, and calculate this angle. So that difference is 3, 2. So if we calculate that, 3, 2, that gives us an angle of 33.69. I'll just abbreviate to 33.7. And the angle 3 is equal to 90 degrees. We can just do that by inspection because we can see that this angle works to 90 degrees. So now I'm going to take angle 0 minus angle 1 minus angle 2 minus angle 3 minus angle 4. It needs to be plus or minus 180 degrees. So 116.56 minus 135 minus 33.7 minus 90 minus angle 4 is equal to plus or minus 180 degrees. So we can isolate the angle 4 on one side by first adding up these three on the left, so 116 minus 135 minus 33.7 minus 90. This works out to be minus 142.14 minus angle 4 equals plus or minus 180 degrees. So angle 4, if we add that to the other side and do a little bit of subtraction, is minus 322.14, or 37.86 degrees. So now if we look carefully at 37.86 degrees, what does that mean? Well, we're going to take this angle here until it is 37.86 degrees. That's going to tell us what our angle of departure is from the pole S4. So we're going to end up with a part of the root locus that looks basically like this. And we can get the angle S3 from symmetry.